Okay, class, good afternoon. So for now, for today, we'll have the band stress, or you have the reinforcements. Web reinforcements. So don't be confused with my notes, since this is not found in your the notes that I already uploaded. At least you have another references for your study, no? So for the band stress, these are the formulas. You have for the actual or applied band stress, you have this formula: mu is equal to V max, that is the shear force. Shear force for big letter V. Oh, big letter. Sometimes you have the small v, that is the shear stress. Okay. Then you have V max over the summation of the diameter circumference times J. J, you already know what is J in the previous topic or example, and multiplied by the D. Okay, so that is for the actual or applied band stress. Next is the maximum allowable band stress. Have this. So for the formula, you have mu allowable is equal to 10.14 square root of FC prime divided by the bar diameter. Okay, that is the bar diameter. So the unit is in megapascal. And then for top bars in tension, you have the maximum allowable band stress, this one, equal to 7.18 square root of FC prime divided by the bar diameters. Okay, so that is for the other than the top bars. For top bars, this is for the top bars in tension. Then other than top bars, you have this formula. Okay, so where your Vmax, that is the shear force maximum in your shear diagram or during your calculation to solve for the shear force. Then you have dB, that is the bar diameter, should be in mm. And then the summation sub O, that is the sum of the bar circumference. So you have the formula: number of bar multiplied by the pi and the bar diameter. So NB is the number of bars. So to be safe, it should be that the applied is less than or equal to the allowable band stress. Okay. Next, we have the shear stress and in the diagonal tension. So in simple beam, subjected to bending, the fibers above the neutral axis NA. So for example, you have this section, the neutral axis acts always at the center. You have the neutral axis NA are in compression, whereas tensile stresses occurs in the fiber below this axis or surface. In addition, these stresses, there are also inclined stresses resulting from the combined effects of bending and shear. So in concrete beams if a concrete beams is reinforced with longitudinal steel only, these diagonal tensile stresses tend to produce crack shown below. So this one. So once you encounter these cracks, maybe in an inspection during earthquake, you can see these cracks, no? This implies to that the stirrups is not actually designed to resist these forces. So to prevent these cracks, it should be that your stirrups distances should be a smaller distance, so that you can prevent these cracks. So if uh, possible, in our NECP code, the distance between stirrups, the minimum is 200 mm. Okay, so these cracks are vertical at the center of the span and become more inclined as they approach the support, where the slope at an angle of 45 degrees. Okay, so vertical at the center or at the midspan, yeah, then going to the support, it is now inclined to 45 degrees. Okay, so the stresses that are caused these cracks are known as diagonal tension. Okay, that is diagonal tension. So for practical consideration, the intensity of the vertical shear is considered to be measured of the intensity of the diagonal tension. Okay, so once you have this kind of cracks, so the stirrups, now you have uh, the stirrups, when that is, you have the effect of diagonal tension, the stirrups now have the inclined formation instead of this one. Okay, so you have the main bar, this is the main bar, and this is now your web reinforcement or stirrups. So that is called stirrups in beams, and then ties in column. Okay, next we have the shear stress. So for the shear stress, you have small letter V. Okay, small, that is the shear stress. For big letter V, big letter, that is the shear force. Okay, so you have the actual shear formula is small letter V equal the big letter V minus divided by the base and the D, depth of the beam. And then for the maximum allowable shear stress of concrete, you have this, that is V allowable is equal to 0.09 square root of FC prime. So if V is less than the V allowable, that is safe in shear. And if the actual V is greater than the allowable, provide stirrups. Since sometimes during design you have this beam, then you have the reinforcement. Sometimes during the design for web reinforcement, you can just have the main bar during the design, but in actual construction, it should be provided with stirrups. No construction of beams that is only provided with the main bars. It should have always stirrups. Okay, even if that is safe in shear. Okay, and then you have the excess shear stress to be carried by stirrups. You have the V prime, that is V minus the allowable. Okay, and then you have the spacing of stirrups. So for the spacing of stirrups, this one, you have the formula. Spacing of stirrups, S is equal to AV. AV is the area of steel to resist shear. The formula is 2 times the area of steel, AST, where your AST is equal to pi times the diameter of the bar square divided by 4. So that is just an area of a circle. Okay? And then Fs, you have the allowable tensile stress of stirrups, Fs. B prime, that is the excess shear to be carried by stirrups, is 1. And then the base, the beam dimension, B and D. From the ECI code, you have the AV mean given in the American Concrete Institute code specification. So you have B, or the base, times the spacing of stirrups divided by 3 multiplied by the Fy. Fy is the yield stress of steel. Okay? So let's have problem, class. So you are to design a 5-meter simply supported beam to support a uniformly distributed total load of 20 kilonewton meter. So self-weight is included. So you have the weight of the beam included. And a concentrated load of 50 applied at the midspan. So this one. Okay. So you are to use FC 9.3 megapascal, and then you have FC prime 20.8 megapascal. Fs, that is the allowable tensile stress of stirrups, that is 124 megapascal. And then the yield stress of steel, Fy, is 276 megapascal. Then you have your N, the modular ratio, that is 9. The base of the beam is 280, 60 mm cover. You have this one. And then you will use the 28 millimeter diameter of the main bar, and for stirrups, that is 10 mm. Okay? And then check for bond and shear stress. So for the illustration, you have a simply supported beam. So you have this beam with a 5 meter length, and then that is simply supported. So you have here a hinge and then a ruler. So for the support reaction, you have vertical here for RAV, and then horizontal for REH, but no horizontal forces or load, so that is 0. And then so you have this one for the ruler, you have RCV, vertical only, that is the ruler. So to solve for the reactions, you can have the summation of forces vertical, or you can have the summation of moment at A or at B. Okay? So but this is a symmetrical beam with a symmetrical load. So due to symmetry, RA and RC is equal. Okay? So you solve for the resultant for the distributed load. So resultant for that is W, big letter W, is equal to W, small w, that is the weight, times the length. So W now is equal to 20 times 5, that is equal to 100. Okay? So therefore, due to symmetry, RA and RC is equal, so you just divide all the loads. So you have now your W here equal to 100. So all the loads, W plus P, that is 150. And then you have RA and RC to be equal, so you divide it by 2. So RA and RC is equal to 75 kilonewton. Okay? So from our solution, you have this. due to symmetry, RA and RC is equal. So you have the WL. No, to solve for big W, you have WL. And then you divide it by 2 so that you have RC and RA equal. And then you have your P. Divide it also by 2. So you have now your RA and RC equal to 75. Okay? So next is you draw the shear and moment diagram. Okay? So you have your RA which is equal to 75 and RC is equal to 75 also. So to solve for the shear, so you have for the shear calculation, for the shear A left, you have at this point 0. And then on the shear A right, that is now you have the RA going up, so that is positive, so plus 75, so you have 75. And then you have the shear B left, so going to this one, B left, well, you have just the left of P, so you have your load W 20 times 2.5. Okay, 20 times 2.5, that is 50. So 75 minus 50, that is 25. So this is straight line, so 0 degree. So for the shear, always have additional 1 degree for the diagram. So this is the load diagram, 0 degree. For the shear diagram, this is in first degree. So 0 for straight and inclined for 1 degree. So from 75, you minus 50, so you have 25. And then you have for B right, shear for B right, so that is minus 50. Okay, you have the concentrated load 50. So 25 minus 50, that is negative 25. So you go down. And then negative 25, you have this, the load, which is left of RC. So 20 times 2.5, so that is 50. So negative 25 minus 50, so that is negative 75. And then you have the shear at right of RC. Right of RC, so you have negative 75, you have RC is 75 going up, positive, so negative 75 plus positive 75, that is 0. Okay? And then for the moment, you have this as first degree. So for the moment, you now have a curve or a spandrel which is in second degree. So first, you have the moment at A, so that is 0. Then going to B, so this is just the area of the shear diagram. So to solve for the area, this is a trapezoid, so you have B1 plus B2 over 2 times L over 2. So B1, that is 75. 75 plus 25, that is 100. Divided by 2, that is 50 times 2.5. So 50 times 2.5, that is 125. Okay? So 125. And then minus this area, which is negative, since that is below the 0 mark of the shear diagram. So 125 minus 125 equal to 0. So this is now your shear moment diagram. So to solve for the maximum moment and maximum shear, you can have the shear and moment diagram, or you can have just solve the uh, shear and moment diagram uh, using your assignment, which is the maximum moment and maximum shear. Okay, so for example, the maximum moment for concentrated load P. At the midspan, you have PL over 4, I think. Okay, PL over 4. And then the maximum moment for the distributed load, that is WL over WL squared over 8, I think. So maybe you can just open your assignment or notes for solving the maximum shear and moment. You can have those formulas, or you can have the shear and moment diagram to solve for the maximum moment and the maximum shear. Okay, so you have here the maximum moment is 125 kilonewton per meter, and the maximum shear you have 75. This one, or you can have the formula for the maximum moment. You have MA is WL squared over 8 plus PL over 4. Okay, so for the maximum moment, you have 125. Okay, so for the resisting moment, first is for concrete. So we have already discussed this with the first topic. So for the formula of the resisting moment of concrete, you have MC is equal to 1 half FC kg BD squared, where your MC should be equate or equal to MA, which is equal to the maximum moment. This is 125 kilonewton meter, and then you convert it to Newton meter, so you just multiplied it by 1 million. Okay, so since that is times 10 power of 6, so this is 6 zeros, so you just have 125 times 10 to the power of 6 Newton millimeter. And then for FC that is given in the problem, that is 9.3, and that is in megapascal, is equivalent to megapascal. Okay, so Newton per millimeter squared is just equivalent to megapascal. And then you have the given base, that is 280. Then to solve for K in design, you have N over N plus Fs times Fc, where your N is equal to 9, and then Fs is 124 and Fc is 9.3. So you have your K equal to 0.403. Okay, then continue. You have to solve for J. J is equal to 1 minus K over 3. So you have there 1 minus 0.403 divided by 3. So your J is equal to 0.866. Then you substitute these values to the formula. MC is equal to 1 half FC kg BD squared. So you have your MC equal to 125 times 10 power of 6, and then equal to 1 half times FC is 9.3, K is 0.403, J is 0.866, then B is 280, then unknown, you have the D. So to solve for D, you have your D equal to 524.43. So you round it up to 525. Okay, so you have now your D. And then next is the resisting moment for steel. You have the formula MS is equal to AS FS JD, where your MS is equivalent also to your MA, which is 125 times 10 power of 6 Newton millimeter. Then Fs, you have 124. J, you already solved J. This one. And then your D is 525. So substitute to the formula. You have 125. Then the AS times Fs times the J times D. So you have your AS equal to 2217.23 millimeters squared. Okay? And then in the problem, you are to use 28 mm diameter bar. So you have to solve for the number of bars from the area of steel. So for the number of bars, you have the formula area of steel divided by the area of the bar. So you have the area of steel 2217.23 divided by the area of the bar, which is pi over 4 times 28 squared. So you have your number of bars equal to 3.6. So round it up. So round it up always. Round up always. Okay? So you have 4 bars. To solve for the spacing, you have this arrangement of your bars. So you have the base. You have this base. You have the 40 millimeter cover times 2. You have this 40. And then 4 diameter bars. Then you have the distance SB. Okay. So you have 29.33 where your bar diameter is 28. So okay. 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 So you can use this arrangement. So next, you are to check for the band stress. Okay. So to check for the band stress, you have this formula. I already discussed this formula. So you have now your Vmax, which is equal to 75 times 10 power of 3. Since that is just 75 kilonewton, you convert that, you have 1,000 Newton, 1 kilonewton. So cancel. So you have 75,000 Newton. Or that is in 3 zeros. So you have raised power of 3. And then you already solve for J, that is 0.866 and D is 522. So you solve for the summation sub O, or that is the summation of bar circumference. So you have the formula number of bars times the pi times the diameter of the bar. So you have 4 times pi times the diameter of the bar. You have now 351.85 millimeter. You substitute that to the formula. Okay. So you have your Vmax 75 times 10 power of 3 divided by the summation sub O, that is 351.85, and then you have J and D. So you have your band stress equal to 0.469. Next is the allowable band stress. You have 7.18 or 1/8 times the square root of FC prime over the bar diameter. So you have 7.18 square root of 20.8, that is given in the problem, divided by the bar diameter. So you have 1.169. So since your band stress is less than your allowable, therefore you have safe band stress. So if that is fail, or if failure, increase your D or decrease the bar diameter if fail during design. Next is to check for shear stress. Okay, so checking for shear stress, you have the formula. Small letter V is equal to big letter V divided by B times D. So you have the shear force, critical shear force on the shear diagram, you at a distance D. So you have to solve this one. Since you have your D equal to 525, so instead of 75, this is 75, you have just this V. Okay? To solve for that one, you can have a similar triangle for this triangle, and then for the rectangle, you have the same value for 25. So you have by ratio and proportion to solve for V, ratio and proportion, you have V minus 25 divided by the distance, this distance. Okay, so for this distance, this is 5 meter you have at the center, so 2.5 or 2,500 millimeter. So minus the D, that is 525, so you have 1,975. So you have V minus 25 over 1,975 equal to 75 minus 25 over 2,500. So you have your V equal to this one. So that is just ratio and proportion. Or you can have V over 1,975 is equal to 75 over 25 millimeter. So you have your V, I think, of minus 25. So that is, I think, 39.39. I think 39. So after that, this is just your V. After that, you add 25. So you have your V, it's the same, equal to 64.5 times 10 power of 3 Newton. This is in kilonewton. So to convert that to Newton, you have times 3. Then you have your B equal to 280 and D is 525. So your shear stress now is equal to 0.439 megapascal. Okay? Next, we have the allowable shear stress. You have 0.09 of the FC prime. So you have 0.09 times the square root of FC prime, which is 20.8. Okay, so your allowable is equivalent to 0.410 megapascal. So since you have your V, or the shear stress, V is greater than the allowable shear stress, so therefore fail. So you are to provide stirrups for this beam. So for the design of stirrups, you have the axis shear. For the axis shear, you have the B prime is equivalent to the actual minus the allowable. Okay? So for the actual, you have 0.439, and then for the allowable, you have 0.41. So you have your B prime, or the axis shear stress, of 0.029. Okay? So next, you have the spacing of stirrups. So for the spacing, you are to use 10 mm diameter bar. So for the formula for spacing, you have spacing S is equal to AV times FS divided by the B prime times B, where your AB is equal to 2 times the area of steel. Okay? Area of steel is equal to pi d squared over 4. So this one. Then multiplied it by 2. So that's the formula. To substitute the values, you have 2 times pi times 10 mm squared. So 10 mm, you have the stirrups diameter. divided by 4 times Fs, that is 124. V prime, you have this 0.029, and then the base B is 280. So you have your spacing of 2,398.75 millimeter. So from the ACI code specification, you have the American Concrete Institute code specification. The maximum distance or the maximum spacing of stirrups is D over 2. D over 2. So you have your D, 525 divided by 2. So you have a spacing of 262.5. So since S is greater than the S maximum from the ACI code, so therefore you have to use S equivalent to S max from the ACI code. Okay? And then check for the AV minimum. Okay, so to check for the AV minimum, you have the formula. For AV, you have this 2 times pi times the diameter of the stirrups divided squared divided by 4. So you have 157.07 millimeter. For the AV mean, you have B times S divided by 3 Fy. So you have your B 280, S is 262.5. So for the spacing, then 3 divided by the Fy, which is 276. So you have your AV mean equal to 88.7. So if you have AV greater than AV minimum, so therefore safe. If that is AV less than AV minimum, so fail. So therefore, you increase